All right, let's get started. Hope you guys all had a nice Halloween and that you are recovered from whatever festivities you participated in. We are now moving into chapter 4. So hopefully the chapter 3 quiz went well yesterday. And just to give you sort of a sense of what's coming, in chapter 4, we're going to take all the derivatives we learned about in chapter 3 and learn how to use those to do all sorts of analysis. So, knowing how to do all that stuff from chapter 3 is going to be really helpful for us in chapter 4. And so today we're going to go through and we're going to learn about local maximums and minimums. There is a lot of information in this section, and so I've condensed it to try to fit into our 75-minute session, but the lecture video that's on Moodle does have more examples than we will be able to do together in class today. So if you're looking for extra examples, you can always go ahead and watch some of those just to get more practice if you would like. So I'm going to go ahead and switch over to the dot cam here. And we're going to start with just like some definitions and some understanding, and then we'll get into the problems. So what we're going to be looking for today are local maximum and local minimums of a function, right? So it's going to be important for us to know when these things occur for all sorts of reasons, right? When functions hit maximums and minimums, you can imagine that that might be important for business or for biology to figure out things like when populations hit maximums, things like that. So this is the first type, the local maxima and minima. Probably on Tuesday of next week, we will talk about something called absolute maxima and minima, which is usually what you think of when you think of maximums and minimums. So we have to think about local maxima and minima and what that means for us. And so for a local maximum, we say a function is going to have a local max if at some point P, it is greater than or equal to values near P. So this idea of near a point is going to become important to us. And a local minimum is the same. So a function is said to have a local minimum at P if f of P is less than or equal to values of f of x near P. So this idea of nearness is going to be important. And some other things that are going to be specific and important to local maximums and minimums is that functions can have more than one local max or more than one local min. So that will be important. And then the local max and min do not have to be the absolute highest or lowest values of the entire function. And so we'll see what that looks like in just a second, but that's typically what we think of when we think of maximums and minimums, right? The biggest value and the lowest value. And that's called absolute maxes and mins, which we will cover, but we're not quite there yet. So what is a local max and a local min? So looking at this picture here, we have a function, it's kind of curvy. So if we're talking about a local maximum, we're looking for a point where it's higher than all the points around it. So this is going to happen when you have sort of a hill in your function. You're going to get this local max, right? Because that's higher than the points near it. Similarly, if we're going to talk about local minimums, we're going to look at the function and look for points where we are lower than points near the point. So we're going to be sort of at the bottom of these cups. So this is a local min. And over here, we have another local min. So again, we can have more than one local max or local min. Here we have one local max, but we have two local mins. And so again, you'll notice that this local min on the right is higher than the local min on the left, but they're still local mins because in the area they're in, they are the lowest point, okay? And so our job today is going to be to find these, right? We're going to look at all sorts of functions and we're going to try to figure out where is the local max, where are the local mins, how do we find them? And so one of the things I want to point out in this picture is if we were to draw in tangent lines at our local maxes and local mins here, they would be horizontal, right? And that is not a coincidence. So it turns out that these local spots that we're going to be looking for have these commonalities that one of the ways we can find them is looking for where we have horizontal tangent lines. Now remember, the slope of a horizontal line is 0. So that's going to be helpful for us. Well, it turns out that when we look for where the first derivative equals 0, right, where the slope of the tangent line is 0, these are going to be really important to us for a variety of reasons, including local maxes and mins. So they have a special name. So this is where our journey of learning about local maxes and local mins will begin. So we're going to start by talking about what's called a critical point. So a critical point P, which is just some value that we've solved for, right, for a function f of x, is a point in the domain of f of x where f prime of p equals 0, so where the first derivative equals 0, or where the first derivative is undefined. So there's two places that we can have critical points, where the first derivative is 0 or where the first derivative is undefined. When do we get functions that are undefined? This typically comes up if we're doing like a quotient rule and we have a denominator, right? We know that we don't want the denominator to be 0. That would be undefined. So that is one case where this might happen. I would say 90% of the time, we're taking the case where we're looking for where the first derivative equals 0. So that's called a critical point. So that's the x value. A critical value is the corresponding y value, right? If you were to take the x value where the first derivative was 0 or undefined and plug it back into the original to get the y value, that's called the critical value. So the critical point is the x number. The critical value is the corresponding y value. Again, we commonly just look for the x value, but just in case, every once in a while, you will have to find the y value that goes with it. So this is where we start. We're going to be interested in practicing and learning about how we can find critical points of our function. And then once we get comfortable with that, we'll learn how to figure out whether they're local maxes, local mins, sometimes neither. But before we can get to figuring out where these are, we have to start by figuring out where these critical points are. Again, this is important because the first derivative equal to 0 is where we have these horizontal tangent lines. All right, so we're going to practice this first. Okay, so we'll do one together. Oh, where's my pen? And then I'll have you try some. So here we have the function 3x squared plus 6x plus 1. We want to find the critical points of this function. So whenever you see that you're looking for critical points, that tells you we want the first derivative equals 0 or the first derivative is undefined if that is possible in your function. So here we have to start by finding the first derivative. So we're doing the power rule here. So we get 6x plus 6, and then the derivative of 1 is 0. Once we have our derivative, we want to set that equal to 0 and solve for any x values. So we subtract 6 to the other side. So we get 6x equals -6. Then we divide by 6, and we get x equals -1. So x equals -1 is the critical point of this function. Now, sometimes when you get your first derivative, it'll be linear and you can solve it like this. Sometimes it'll be squared and then you have to factor. It just depends on the function. But that's what we're going to practice first. So we're going to start with these two practice problems. The first one, 2x cubed minus 3x squared minus 36x plus 14. We want to find the critical points. When you find the first derivative here, you will have to either factor it or use the quadratic equation, but the roots are integer numbers, so you're not going to end up with anything too crazy. And then the second one I want you to try is x squared over x minus 2. So you'll have to use a quotient rule here and think about how we figure out where it equals 0 and where it will be undefined. Okay, so a little algebra here, but the first step is to find the derivative, which hopefully from all the practice in chapter 3 is not too crazy. So I'm going to give you about 3 minutes to try out these two functions and see if you can find those critical points, and then we'll go through them together. right, take about 30 more seconds. All right, so for number 2, we have a polynomial function and we're looking for the critical points. So we're going to start by finding the first derivative. So from this first term here, we're going to get 6x squared. So again, the 3 comes down to multiply the 2. We subtract 1 from the power minus, now here we'll have 6x from the second term. And then the derivative of 36x is 36, and the derivative of 14 is 0. So we want to know, when does that equal 0? There's 2 different ways that you can do this. Well, there's probably more than 2 ways, but the 2 most common ways are to factor this or to use the quadratic equation to solve. Either is fine, you will get the same roots. I'm just going to go over factoring just so if it's been a while, we can remember how to do this. So for me, I always try to pull out the number in front of the x squared term to make it a little bit easier. So I start by factoring out a 6. So I'm left with x squared minus x minus 6 equals 0. So I just pulled out the 6. And now I'm looking for 2 numbers that multiply to give me negative 6, but add up to give me negative 1, the middle term, right? So I'm going to do x minus 3, x plus 2. So minus 3 times positive 2 gives me that negative 6. And minus 3 plus 2 gives me the cross term of negative 1. So now I have 3 factors. I have 6, I have x minus 3, and I have x plus 2 equals 0. So I have to set each factor equal to 0 to solve. If I set 6 equal to 0, there's no solution, right? 6 will never equal 0. But if I do x minus 3 equals 0, so this factor, I get x equals 3. So that's one solution that makes that 0. Then I set my second factor equal to 0. So x plus 2 equals 0. That gives me a solution of x equals negative 2. So I have 2 critical points here at x equals 3 and x equals negative 2. There's nowhere where the first derivative is undefined here, so I'm not worried about checking that at this point. Okay. Example 3, we're going to start off and do the same type of process, but obviously we have a different type of function. So to find the critical points, our first step is going to be to find the first derivative. But what I notice here is that I have one function over another function, so I have to do a quotient rule. So when I do the quotient rule, my top function is f, and my bottom function is g. I take the derivative of each piece. The derivative of x squared is 2x. And then the derivative of x minus 2, the derivative of x is 1, and the derivative of 2 is 0. So when I plug into the quotient rule, I'm going to do f prime times g. So I'm going to have 2x times x minus 2 minus g prime times f. So 1 times x squared divided by g squared. Okay, so I'm going to simplify the numerator a little bit because now simplifying is going to become important because I'm actually solving for something here. So I'll do this in a couple steps. So here I'm going to distribute the 2x through this parenthesis. So I get 2x squared minus 4x, and then I still have this minus x squared over x minus 2 squared. Now in the numerator, I have a 2x squared and a minus x squared. So those are going to simplify into 1x squared minus 4x over x minus 2 squared. Okay, so this is in pretty good shape to now use to find my critical points. So again, critical points happen at x equals 0 or if the function is undefined. If you have a rational function, so you have something over something, what we can do to figure out where it equals 0 is set the numerator equal to 0. Okay, so let's say derivative equals 0 when the numerator equals 0. So here I can factor out an x. So if I pull out an x, I'm left with an x minus 4, right? And so now I set each factor equal to 0. So one of them is x equals 0. That's the first factor, and that's just the solution. And then I also have x minus 4 equals 0, which when I solve gives me that x equals 4. So x equals 0 and x equals 4 both give me the place where the derivative equals 0, because if the numerator equals 0, then the fraction equals 0. I also, in this case, have to find any places that we are undefined. That's the other way we have critical values and critical points. So how do I check if a function's undefined? Well, if it has a denominator, I want to see, is there anywhere where the denominator will equal 0? That was what will give me something undefined, because then the denominator will go to 0, the whole thing will go to infinity. So I have x minus 2 squared, so that will be 0 when x equals 2. That'll make that factor equal to 0. So I have 3 values that are critical points here, x equals 0 and x equals 4, which made the derivative equal to 0, and x equals 2, which makes the derivative undefined. So again, when you're doing a quotient rule, you always have to check the denominator to see if there's a place that will make it equal to 0. Okay, so those are our critical values here. This is sort of a common first step for a lot of the problems we're going to be doing. Now, for these 3 problems we just did, these are all algebraic. So we started with a function and we did the algebra to find the first derivative, set it equal to 0 and solve. There are a couple of other ways that we can look for critical points. So I'm quickly going to review how we might do this if we had, say, a graph and then subsequently a table. Okay, so suppose that we are given the derivative on the graph below. Okay, so this is a graph of the first derivative, not of the original function, right? We want to use this graph to determine the critical points on the interval -2 to 8, right? So that's what's given in this picture. So if we want to find the critical points of the original function, we want to know, where does the first derivative equal 0, right? Critical points, first derivative equals 0 or undefined. This graph is continuous, so it's defined everywhere. So we're really asking, where does the derivative equal 0? Since this is the graph of the derivative, we are looking for the places where we cross through the x-axis. Because if the derivative equals 0, that means that the y value is 0, and we are trying to find the x values where that happens. So that happens here at 0, again at roughly 3.1 and 6.2, so that's probably pi and 2 pi. But the idea here is to just label the points. And so on a graph, we are looking for where this function crosses through the x-axis. Okay, so if you are given a graph, one of the first things you're going to want to do is you're going to want to try to figure out what graph you have. Is it a graph of the derivative? Is it a graph of the original function? Then you can answer the questions that you have. All right, what about if we have a table? So I want you to try to think about this. I'm going to give you a minute to see if you can figure this out. So here we have a graph. We have a table. We know that the function and the first derivative are continuous, but we want to know where we might have a critical point if we have a table of values of the first derivative. So these are all values of the first derivative. We are trying to think about where the critical points may be. Remember, that means we're interested in where this might be equal to 0. So I want you to take a quick minute, think about this, see if you can figure out where you think the derivative might be equal to 0, any places on here, and how we might write that. So take 1 minute, look it over, jot it down, and then we'll go through it together. All right. So again, now when we have tables, we always want to make sure we know what type of function we're looking at. Here we have the first derivative. So if we're looking for critical points, we're really thinking, where does the first derivative equal 0? So again, you have to remember that the independent values are on the top and the dependent values are on the bottom. So here, if I look across the bottom, I see a place that specifically is 0, right? F prime of x is 0 when x equals 6. So this is one place where we're going to have a critical point for sure, right? Because we know it equals 0 there. That one is a little more obvious. It turns out that there's also another sort of hidden place that we are likely to have a critical point. So since this function is continuous, we know that in order to get from -4 to 5, right, so around this, that we had to go through 0, right, because you have to cross through to change signs. Over here, I want you to notice that the y value went from 2 to -1. So in order for a function to change from positive to negative, it would have to go through 0. So that means that there's another critical point somewhere between x equals 10 and x equals 12, right? So when we have a table and we're talking about critical points, which we'll be looking at all sorts of examples, right? We are looking for places where we change signs. So that happened here from -4 to +5, but we were lucky because we were explicitly told where the 0 was, right? But here, it was a little more hidden. We changed from positive to negative, right? But we don't know exactly where it happened, right? It could have been 10.1, it could have been 11, but we also have to find all the places where we change signs because we might be sneaking through 0, okay? So those are the different ways we look for critical points. We can do it algebraically, set it equal to solve. We can look at it graphically. We are looking at the picture for zeros, or we can look on a table, okay? So that's going to be our first step for all of the things we're doing. We're always going to start by finding our critical points. So once we have critical points, there's sort of 3 different ways that we can figure out if they are local maxes or local mins. And so there's 3 different tests that we're going to look at and figure out how to use. The first one is when we just have the original function, right? So here we're given the function 4x cubed minus 6x squared minus 72x plus 12. We also have a graph of this original function, okay? And so this first test that we're going to use to figure out what our critical points are is we are going to use the function f of x. We're going to have some picture of it in some way, and we are going to visually locate where our, different critical points are going to be. And so the first test has 3 sort of properties that we are going to use. So if f of x changes from increasing to decreasing, so it's going up and then it's going down, right? Then we're going to have a local maximum. right? If f of x changes from decreasing to increasing around our critical point, right? We're going down and then we're going up. Then we're going to have a local minimum. If f of x does not change from increasing to decreasing or decreasing to increasing, then we have neither. So what does this look like in practice, right? So here we are just sort of eyeballing what's happening, or if we have this on a calculator, we can trace it. But we're looking for critical points visually. Again, horizontal tangent lines here. So there's two places that this happens, right? So roughly -2, oops, we're counting by twos here. And then again over here at 3. And so what we're saying is, okay, at -2, I'm increasing first and then decreasing after my critical point, right? I'm going up and then down. So x equals -2 is going to be a local max. If your function is decreasing and then increasing, then you're going to have a local min. So x equals 3 is a local minimum. Okay, so what we're doing is we're literally looking at the picture to see, does it look like a hill or does it look like a cup, right? To figure out if our critical points are local maxes and mins, right? So when we do this, the way that we're going to do these problems to practice this test is we're going to identify the critical points algebraically. So we'll find where the first derivative equals 0. Then we're going to sketch a graph to figure out, are they local maxes or are they local mins, right? And we're just going to look at it visually, and that's going to help give us information and help us figure out what type of critical point it is. So let's start with this example here, where I haven't given you any sort of picture, to see if we can apply this. So here we have the function 3x squared plus 6x plus 1. What I would like you to do is I'd like you to find the critical points by finding the first derivative and setting it equal to 0. Then once you have those x values that are the critical points, I want you to graph the original function. So you can do this on a calculator. You can plug in a couple values to get a general sketch of the graph. We know it's going to be a parabola. And then once you know what it looks like, you should be able to state whether that critical point is a local max or a local min. Okay, so again, the first step is to find the critical point. And then the second step is to use the picture to determine what kind of critical point it is. So take a quick 2 minutes, see what you can figure out, and then we'll look at it together. Okay, take about 30 more seconds. All right. So again, we want to start by finding the critical points. So I'm going to take the first derivative of my function, which will give me 6x plus 6. I want to know, where does that equal 0? So I have 6x equals -6, divide both sides, and I get x equals -1. So I know I have a critical point at -1, and now I want to figure out what kind of critical point is it? Is it a local maximum, a local minimum, or neither? And so with this first test that I have, it says, well, hey, you can look at a picture of the graph. So if I were to graph this particular function, it's going to look roughly like this. So it's a parabola. I can see that right around -1 is where my horizontal tangent line is. And again, I'm graphing the original. And so visually, I can look at this and I see that this point is going to be a local minimum. Okay, so by graphing it, I can figure out what type of critical point x equals -1 is. Okay, so here, this is a local minimum. Now, I do want to sort of talk about the fact that local maximums and local minimums are pretty easy to visually identify because maximums look like hills and minimum looks like cups. But what about this like neither case, right? So what would it look like if we had neither? So sometimes we have functions that do something like this. So maybe we come around, right? And so here we have a local min, we have a local max, but then we have this spot here, like that's right in the middle. So we're going to have a horizontal tangent line there. This will be a critical point, but this is not a local max or a local min. It's just sort of a weird flat spot. They don't happen too often, but that's what a neither case would look like. So it just kind of flattens out and doesn't distinctively have a local max or a local min. Okay. So let's look at the next type. We're still using this particular test. This is one of 3 types of tests we'll use, where we're going to be relying on the original function and thinking about where the original function's increasing and decreasing to figure out whether critical points are local maxes and mins. So let's look at a table. Okay, so we have this table. Again, all functions are continuous. Notice here, this table is the original function. This is f of x. And we also know that f of x has a critical point at 5 and at 11, right? So at 5 and 11, we know that we have critical points. Now, we don't see these critical points on this table because 5 and 11 are not defined, so we don't know the values. But we want to use the behavior of f of x to try to figure out if these critical points are going to be local maxes, local mins, or neither. Okay, so what I want you to do is I want you to take a minute and think about whether this function's increasing and decreasing, how it changes, and what that might tell us about the critical point. So take a minute just to look it over and think about it, and then I'll go through it. Okay, so since we know that there's critical points at 5 and 11, we sort of have 3 distinct chunks of data, right? So we want to look at what's happening before 5 and after 5, before 11 and after 11. So when I look at these values, 4, 8, 10, okay, those values are increasing. So before I get to 5, I am increasing. Okay, what about after 5? So here I have 8, 5, 2. So those numbers are going down. So from this chunk, my values are decreasing. And then here after 11, I have 7 and then 10. So we're increasing again. Okay, so here my original function is going from increasing to decreasing through 5. That means we're going up and then coming down, right? So increasing, and then we have a critical point, and then we're decreasing. So if we go from increasing to decreasing, that means that our critical point is most likely a local maxima, okay? When you go from increasing to decreasing. If you go from decreasing to increasing, you are going down and then up around your critical point. So decreasing to increasing, that means your critical point is most likely a local minimum. So x equals 5 is most likely a local max, and x equals 11 is most likely a local min. So that is how we would most likely use those particular rules that we're looking at to use that test. So if you have information about the original function, f of x, you want to know where it's increasing and decreasing to help you classify your critical points. Okay. Now, the next test that we're going to look at to classify critical points is the first derivative test. So again, the test that you choose to use to classify the critical points really depends on the information you have. Sometimes you can choose any of the tests and you'll be fine. And sometimes you sort of have to use one of them based on what you're given. So what does the first derivative test look like? So we're going to do an example in a minute, but let's look at the rules that we're going to use for the first derivative test. So we know that the critical points of the function of this interval are going to divide it up into these subsections that are going to give us this domain for the first derivative test. And then within that, we're looking for if the first derivative changes from positive to negative, then we know our critical point is a local maximum. If our derivative changes from negative to positive, then our first derivative critical point here is going to be a local minimum. And this tracks directly with increasing, decreasing, right? If your first derivative goes from positive to negative, your original function goes from increasing to decreasing, local max. So that's the same as what we were doing before. If the derivative doesn't change, then your critical point is not a local max or a local min. So that's like the weird flat spot. So how do we employ this test? What does this look like? What do we do with it? So we're going to look at this function here. And again, we're thinking about what are the critical points, and then how do we use the first derivative test? The critical points we've already done, so we'll do this a little quickly here. So we've done this function. So we have 12x squared minus 12x minus 72. So we have our first derivative. We want to know where does that equal 0. So our first step is to find our critical points. So if we pull out the 12, we're left with an x squared minus x minus 6 equals 0. Okay, this particular function we factored before with a different constant, but let's do it again anyway. So we have x minus 3, x plus 2, right? That's going to give us what we need here. And so we have 3 factors. We have 12, we have x minus 3, and we have x plus 2. 12 equals 0 doesn't have any solutions. So we end up with x equals 3 and x equals negative 2. Okay, so these are our critical points. Now, to use this particular test, the way we want to set this up is we need to look at the intervals of the first derivative as divided by our critical points. So we set up this number line, and we're going to put them in order like you would a number line. Okay, so we have negative 2 and 3. Those are my critical points. And I'm thinking about what is going to happen within the derivative. So I know that since these are critical points, the derivative is 0 at negative 2 and at 3. What I need to do now is I need to use a test point for each interval here. So I've less than negative 2, between negative 2 and 3, and greater than 3. Those are the places. And so I can pick any test value that I want that's on that interval that's not the critical point. So for example, I'm going to pick 0 as my test point for between -2 and 3. I'm picking 0 because it's a point that's easy to plug into the derivative. But you could pick -1, +1. You want to pick something that's going to make the work easy. So if I plug 0 into my first derivative, I get 0 minus 0 minus 72. So I have minus 72 is the value, which is negative. So I'm going to put a negative on top of that. Now I'm going to also test something that's greater than 3. So again, I'm going to pick a value that's easy to work with. I'm just going to pick 4. And we're going to plug 4 into the derivative function here, right? And so when you do that, you are going to get positive 72. So that's a positive value. And then finally, I have to pick something to the left of -2. So here, what did I pick? I picked -3. So I plug -3 into the derivative. You can plug it into the factored version or the regular version. You'll probably be doing that part on your calculator. And you're going to get positive 72. So positive. So these are called test values. We need a test value for each interval. And then we're going to use this to correspond to these signs. Okay, what does that mean? So remember, -2 is our critical point. We're looking at what's happening around -2. So this first derivative is changing from positive to negative. If the first derivative changes from positive to negative, then that critical point is a local max. Okay. Our second critical point is x equals 3. So we want to see what changes around 3 on that interval, the interval to the left to the interval to the right. Here I go from negative to positive. If your first derivative goes from negative to positive, then we have a local minimum. Okay, so now we are using the first derivative to classify our critical points. Could I have just graphed the original function like I did before? Yes. Is this another way to do this? Yes. Is it helpful to make sure we know all the ways to do this? Yes. What I recommend is once you've classified your local maxes and mins, graph the original, make sure it matches with what you are saying. Okay, so I'm going to have you try another one. Again, we're really interested in what is going on with local maxes, local mins, slightly different function, not too far off. So you can try this out, set up your table again, see what happens, right? So I'm going to give you about 2-3 minutes, right? Again, first step, find the critical points. They should seem familiar. We've done this function before. Second step, you're going to set up your first derivative number line. You're going to pick test points. You're going to put them in. Then you're going to figure out how the first derivative is changing, and then you can classify your critical points. Okay, so take 2 minutes, see if you can try that out. Again, this one is meant to be particularly easy, so if you feel like you've discovered something easy, you probably have. It's designed that way. Okay, try it out, and then we'll go through it together. All right, take about 30 more seconds. Okay. So again, our first step here will be to find critical points. We're going to start by finding the first derivative here. So we have 6x squared minus 6x minus 36. We want to know, when does that equal 0? So if we factor out a 6 here, we have x squared minus x minus 6. Hopefully that looks familiar to you. Equals 0. So here, when we factor it, we're going to have x minus 3, x plus 2 equals 0. So our critical points here are x equals 3 and x equals negative 2. Okay, so we're going to set up our number line. Negative 2 is to the left of 3. We know that at those particular values, the first derivative is 0. And now we need to do some test points. So one thing I want to point out is another way that you might approach this. It's completely up to you. But what you can do is you can look at the factors and just look at the signs instead of plugging something all the way in, if you prefer to do that. And what I mean by that is if we take 0 and we plug it into this first factor, 0 minus 3 is negative, 0 plus 2 is positive, negative times positive is negative. So without actually finding the value, I can still figure out the sign of my test point. And that's just a matter of preference. If you prefer to get the value, that's fine. If you prefer to just think about what the sign will be, that's fine too. So for example, if I use a test point of 4, 4 minus 3, that's positive. 4 plus 2, that's positive, right? Positive times positive, positive. So I didn't have to get the value to know that at 4, I'm going to be positive, right? Similarly, if I plug in a negative 3 minus 3 is negative. Negative 3 plus 2 is negative. Negative times negative gives me positive. Okay. So you can reason through that way, or you can do the full value. It's up to you. And now again, we're interested in how our signs change around the critical point. So my critical point of negative 2, I go from positive to negative. If I go from positive to negative, I have a local max. And at positive 3, if I go from left to right, my derivative goes from negative to positive. If I go from negative to positive, I have a local min. Okay. So that's the algebraic version of the first derivative test. So if you have a function, that's the process. You find the critical points, then you draw your number line, you do some test points, and you see how we change. This also can come up with things like graphs and tables. So let's see how that might apply to what we've just been talking about. Okay, so here the derivative is given in the graph below. Okay, it's important to note that this is the derivative. And we're looking for local maximums and minimums on this function. So this is the same graph we looked at before. And now we're going to classify our critical points. So we said the critical points happen when the first derivative equals 0. So that happens at 0, 3.1, and 6.2 roughly. So these are the 3 places where we cross through the axis. And so those are our critical points. if we want to figure out if these are local maximums and minimums for f of x, right? So for the original function that we do not have, we need to use that first derivative test. And so in order to use the first derivative test, we need to know if we're changing from positive to negative, negative to positive, or neither. So how do we incorporate that here? So when we talk about the first derivative being positive or negative, we are talking about if the function is above or below the x-axis. So here, the function is positive to the left of this particular point, and it's negative to the right, right? Because we're above, positive, below, negative. If we change from positive to negative, that makes your critical point a local max. So what does that mean? That means on the original function that we do not have, we don't know what it looks like, we don't have it, but at x equals 0, the original function has a local maximum. And we are able to figure that out using this first derivative test. Okay, similarly, looking at our second critical point here, a little bit past 3, to the left, I'm negative because I'm below, and to the right, I'm positive because I'm above. If around my critical point, my derivative goes from negative to positive, that makes my critical point a local minimum. Okay, again, this just goes back to the rules. If you go from negative to positive, you have a local minimum. Finally, at my last critical point, again, when I'm above, I'm positive. When I'm below, I'm negative. So from left to right, I go from positive to negative. So I have a local max. So when I have a graph of the first derivative, I have no choice but to use the first derivative test because I don't have the original function to look at to see is it a max or a min. And we cannot look at where this has maxes and mins because that's not what we're asking. We're asking where the original function had maxes and mins. So we use this to find critical points, and then we use how it changes to figure out what type of critical point it is. Okay, this does take a little practice to get used to, but it does come along as we practice more and more. Similarly, right, let's look at a table. So here we have a table of a derivative. So this is f prime of x. And we want to figure out where we have critical points, and then again, if they're local maxes and mins. So we already determined where the critical points would be before, but I'll just remind you. So we have one at 6, right? Because the derivative is 0 there. And then we have another one between x equals 10 and x equals 12. So there's a critical point somewhere in there. And we know that because our table changed signs. Okay, it doesn't matter if it goes from positive to negative or negative to positive. If your derivative changes signs, it had to go through 0. So how do we figure out if these are local maxes and mins? Well, again, we can use the first derivative test. So here and here are the 2 points around this first critical point. This was -4, and then it changed to +5. If your derivative goes from negative to positive, that means you are decreasing and then increasing. So this critical point is a local minimum. Okay. Over here, we're going from positive to negative. So to change from positive to negative, that tells you that this critical point is going to be a local max. So we would say something like we have a local minimum at x equals 6 and a local maximum somewhere between x equals 10 and x equals 12. Okay, so when you have information about the first derivative, we are looking at how the sign changes within that first derivative. Okay, now the last test that we use here is the second derivative test. Okay, so again, it really depends on what kind of information you have, but here we have the original function. Could we graph it? Yes, we could use that first test. Could we find the first derivative and classify positive to negative, negative to positive? Yes, we could also use that test. But we could also use the second derivative test. So how does that work? So the second derivative test asks us to plug our critical point into the second derivative and then look at the sign of the second derivative to think about what type of critical point it would be. And the reason that that will work is because if the second derivative is positive at our point, we're going to be concave up, which makes it a minimum. Okay. And if we're concave down, that's going to make it a maximum. Oh, these are backwards. I don't know how I wrote those backwards. Okay. So if you're concave up, you look like a cup. That's a minimum. If you're concave down, you look like a hill, and that's going to be a maximum. Okay, so what does this look like in practice? So again, first derivative to find critical points. So we have 12x squared minus 12x minus 72 equals 0. We will have factored out the 12. Right, so then we factor it again. And our critical points are x equals 3 and x equals -2, right? So we've done this problem before. But then how do we use the second derivative test? Well, we have to start by finding the second derivative. And when we find the second derivative, you want to go from the unfactored version. So we have 24x minus 12. So there's our second derivative. What we need to do is we need to plug each of our points into the second derivative to determine if the second derivative will be positive or negative at that point. So there's two different times we have to do this. So first we plug in the 3. Okay, and let me emphasize this. What we are interested in is the sign of the second derivative. The magnitude, which is the number we're going to get, is not what we're interested in. We're just interested in if it's positive or negative. So you might be able to save a little time by just looking quickly. You might know whether it's positive or negative, or you might have to plug it in. Okay, so here when we plug in a 3, we're going to get 60. Now that 60 doesn't mean anything, but the fact that it's positive does. So since this is positive, positive, that tells us that the second derivative is concave up, right? So here we are concave up, which tells me that 3 is going to be a local minimum, right? Because we are concave up, we see that that's going to be a minimum. And again, this is a local minimum on the original function. Similarly, we need to test the other critical point we have, -2, into our function. So I'm just going to do it up here for space. So if we plug a -2 into our second derivative, we have 24 times -2 minus 12. So again, the number itself doesn't matter, but the sign does. So this is going to give us -60. And it's the negative that's important, because since we are negative, right, that tells us that the original function is concave down, which means that -2 is a local maximum. So we are relating this back to our understanding about the concavity, but I want to be really clear. When we talk about local maxes and mins, we are talking about local maximums and minimums of the original function, right? Which we may or may not have. We do have, let's see, from when we started, we did have a picture of it, right? That was like the first problem we did. So we do know what this particular function looks like, and we are expecting a local max at -2 and a local min at 3, which is what we found here, right? But if we didn't graph it, we could still figure out that these things exist. like I said before, it's a good idea to check your work by graphing the original function if you can to make sure it matches up, okay? So let's go ahead and try this one, right? So again, similarly, your second derivative will be slightly different than before, but your critical points will be the same. So start by finding the critical points, finding the second derivative, plugging them in, matching it to the concavity, and then determining if they are maxes and mins. It'll take about 2 minutes, and then we'll go through it together. All right. So again, we start by finding the critical point. We've done this particular one before, so we know what the critical point is, but as a quick review, we take the first derivative, we get 6x plus 6. We want to set that equal to 0. And then we solve for x. So we bring the 6 over and divide by 6, and we get x equals -1. Now, we want to use the second derivative test to determine what type of critical point this is. And this is a really good example because something really interesting happens here. So when we find the second derivative, we just get that the second derivative is 6, right, from the 6x term. Now, you might be thinking that we can't use this because we can't plug in the -1, but actually we can, because the second derivative equals 6 for all values. That means it also equals 6 when x equals -1, which means the second derivative is positive everywhere, right, for all values. And if the second derivative is positive, that means the entire function is concave up. If it's concave up, that makes your critical point a local minimum, okay? So even if your second derivative doesn't have an x in it, you can still use the second derivative test to figure out what type of critical point this is going to be, okay? If there's an x value, you do have to plug it in for x, but if there's not, then you know that the function is either entirely concave up if the second derivative is a positive constant, or concave down if it's a negative constant. So you can still use it, okay? How else does the second derivative test help us? So let's look at 2 more quick examples. I'm going to skip number 4. Number 4 is done the same way. It's just a new function. You would find the critical points and then find the second derivative and plug them in, just like we did before. The difference is this function is a product rule. But I want to do the other 2 that are not ones we've looked at before. So for example 5 says, suppose that f of x is continuous and a differentiable function, and we know the following information. So we have just a whole bunch of data points here, and we want to use this information to determine where f of x is likely to have a local max and a local min, okay? So here we have to figure out how to use this information, and so I kind of want to group some things together. So this is information about the original function, right? So when x is 1, y is 10. When x is 7, y is 1. Then we have some information about the derivative here and here. So the derivative at 2 is 4, the derivative at 4 is 0, the derivative at 9 is 0, and the derivative at 12 is 8. And then we finally have information about the second derivative over here. Okay, so this is the second derivative. This is the first derivative. And then we have the original function. Okay, so we have 3 different types of information. So I want you to remember that if we're looking for local maximums and minimums, the first thing we're looking for is critical points. And so critical points happen when the first derivative equals 0 or if the first derivative is undefined. So we really want to start by looking at what kind of information we have about the first derivative. So here I notice that f prime of 4 equals 0. And f prime of 9 equals 0. So that means I have a critical point at x equals 4 and x equals 9. Okay. And so what I want to do is think about the other information I have to see if I can figure out what type of critical points these would be. Now, I don't have enough data of f to figure out if I'm increasing or decreasing. I only have 2 points, right? So that's not going to be super helpful here. If I had a lot more points, I might be able to figure that out. For the first derivative test, I have a data point to the left of 4, so that's helpful, but I don't have one to the right of 4. The next data point I have is 9, so I would need something between 4 and 9 to be able to use the first derivative test. But then if I look at the second derivative, I notice that I've given values at 4 and 9. Those are the particular points where I had critical points. So here I can use the second derivative test to figure out what type of critical points 4 and 9 are. So the second derivative at 4 is negative. If we're negative, we're concave down. So that tells me that 4 is a local max. The second derivative at 9 is positive at 3, which means it's concave up, which makes 9 a local min. So I had to use my information about the first derivative to find where the critical points are, but then I had to use the values of the second derivative to figure out what type of critical point it is, that it's a local max at 4 and a local min at 9. Okay, so when you have information presented like this, you really need to think about what it's telling you and figure out how to sort it in a way that helps you use these tests to leverage this information. Okay, and then let's see, the last example we have, suppose that f of x equals ax squared plus bx minus c, where a, b, and c are non-zero constants. So they're just numbers. What has to be true about a for this function to have a local minimum? Okay, so there's something that has to be true about a in order for this function to have a local minimum. So what I want you to do is I want you to take 2 minutes, so we have enough time to go over it. See if you can find the first derivative and the critical point. See what you know about that, and then see if you can find the second derivative and if that helps you answer this question. Okay, so I'm just going to give you a quick 2 minutes and then we'll go through it. All right, so let's take a look at this. So if we wanted to talk about the critical point of this function in sort of a generic way using a, b, and c, we would find the first derivative, which will be 2ax from the first term, plus b from the second term, and then c will be 0. If we set that equal to 0, we could then solve for x by subtracting b over and then dividing by 2a. So our critical point is x equals negative b over 2a. But the question here is, what has to be true about a for this function to have a local minimum? So there's nothing we can really say about the actual critical point to make this a minimum. So we're going to use the second derivative here. So the derivative of 2ax is 2a. The derivative of b is 0. So if we need this particular x value to be a minimum, we can manipulate the second derivative because there's no x in here. We're not plugging this in. This is like the one we looked at with a 6. So in order for this to be a local minimum, that means the second derivative has to be positive. Okay. In order for the second derivative to be positive, we would need 2a to be greater than 0, which means that a has to be greater than 0. If a is a positive number, that will make the second derivative positive, which makes the original function concave up, which makes this particular critical point have to be a local minimum. Okay, so as I said, there's more examples done out on the video. If you want to see example 4 done out, that one is on the video. It's linked in Moodle. I would practice these early in the week. They can get a bit long, and trying to learn to sort through different tests takes a little bit of time, but try your best, and hopefully you'll be able to figure them all out. Okay, I will see you guys on Thursday.